So the problem we are going to solve today is going to look like this. I'm going to rewrite it. This is a problem we solved in the morning section, but I will alter it in a small way. So it's not an identical problem. And so we are going to talk about how to solve it. So I will put both problems for as an example, just the solutions, all right, and the videos for you. So you see two separate problems when you want to practice. But this one is from the morning, and I will do a similar one for us today. So let me just go back and then, okay, I will define the problem, and then what I would like you to do, which I plan to also ask you to do in the final, I will ask you to draw the problem that I will already have provided to you, but I will ask you to draw it yourselves. And then I will give you points for doing that. And then I will ask you, okay, and then I will ask you to, apologize for this, kind of hot, yeah. And then I will ask you to also write down and give you points for this, for all of the data that I'm giving you. And also I would like to, I will ask you to write down the thing that what you are supposed to find in the solution as part of the solution. And you're going to get points for this. And I will do that, not because I will do this not because it's anything unique, but because you're going to benefit as you are going to try to solve your problem. Okay, so here we have 3 transmission lines. All right, and I will, so let me write first of all here, it's an example. And all of the problems that we are solving are examples on matching. Now, matching, which we explain what expresses by saying matching, is that you have a transmission line, you have a load at the end of the transmission line, and then you're trying to find a way to match the load to the line. And we're going to talk about this again to remind you while I'm going to set up this problem. So the problem is the following. We have a transmission line here. In fact, we have more than one transmission lines. This is your input line. This is the line that connects with your source. And the source is given to us is this. All right, so it has an amplitude V naught. And what they're giving to us is, and I will write everything that is given, will be the value of the amplitude of V naught, and which also we call the phasor for the source. And also they may give you the amount of power that the source, the maximum power that the source can deliver to the load. I will write this down. So for now, you have a transmission line with a Z naught that is connected to another line here. All right, so that's another line that has a characteristic impedance of Z1. And then there is a third line at the end. And that is the last line that connects to a load. And the load for us is given. And in fact, they will give you the following thing. They will tell you that the load here is a resistor. That's how they may give you the load. It's an antenna, as a matter of fact, and they will tell you the antenna has a resistive value, and then it has a capacitor. also is like the equivalent. They will find an equivalent circuit for the antenna, and that will be a resistor R and a capacitor C. All right, and then they will tell you in between here, you have a line so the front line has a length, all right? They may tell you that this length is D1, and let's assume that this length is 0.2 lambda. Then they tell you that the lines are connected, obviously, and then they will tell you that this length, the second line, they would like you to find it. This is D2. So obviously it's not given. And then they will tell you that you have another line at the end, and this line has a characteristic impedance. Let's make it a little simpler to make it like Z naught also, even if it might be different, but Z naught. And that has a length D3, which you also do not know. All right. And then they tell you that I want you to, so let me see what is given in this problem. Given. They give you information about the source that V naught, say for example, is 1 millivolt, or not, this is too small. So say 1 volt, even if we don't, it's not necessarily that important for us. And then they give you that the maximum power that can be delivered by the source to your, but not to whatever can be delivered, the maximum power that can be delivered by the source is, say, 0.5 milliwatts. Okay? And that is number one. Number two, they give you the D1 is 0.2 lambda. Number three, they give you that Z naught is 50 ohms. They also give you that RL is 80 ohms. And they give you that CL is picofarads. So let's say that it's about 0.5 picofarads. All right. And then they tell you that I have a frequency F, which is 10 gigahertz. All right. And they tell you in that frequency, for that particular frequency, we want you to design this network, find, therefore, so we need to find the following. Find D2, find D3, and find Z1. So that you receive the RL dissipates all of 0.5 milliwatts. So practically, they're telling you that we want you to find these three parameters, specify them, so all of the power goes to your RL. And your RL will be practically the radiation resistance of your antenna. So whatever goes and is absorbed is not a real resistor, but whatever goes to that, which is an equivalent, the radiation resistance of the antenna that is radiated. That's what it means, all right? So that I will put as a parenthesis here. So that can be the radiation resistance of an antenna, which is given to you because there is another designer who is going to design this antenna, or who has designed it, or maybe they purchased the antenna from a supplier. And then capacitance is the capacitive load of the antenna. So it's called the capacitive load of the antenna. Why do you think the antenna is going to have a capacitive load? Do you know how antennas look like? Have you seen an antenna? This one. That's an antenna, it's a dipole. All right. This is connected here. So what is a dipole? A dipole antenna. So I'm showing everybody here. This is a dipole antenna. All right. This is from the speaker here, from the microphone rather. So this one, the way it's a very simple antenna, very low cost. All right. This one is not. Does not have a dipole. This one has, if you were to scratch the paint off, you will see what we call a slat antenna. A slat antenna is something that is created with two conductors coming very close to each other. So it's like a gap between two, like it's a gap. You have a metal, a ground, and then it's like you scratch you make a deep scratch that separates the two grounds. That is something that can radiate. All right, so they do it on purpose here because it's flat. But this one, so it's more versatile, it's simpler. This maybe it's 1 cent when you purchase it. So when you buy something like that, you don't pay like an iPhone, all right, or something like that. Okay, what is a dipole? A dipole, just so you see what a dipole antenna, so assume that you have a dipole antenna here. What is a dipole antenna? It's a very simple one. It's one of the very first that people found. So practically it's like the ideal dipole will look like this. So it's like two metals separated, and then here you feed them with a transmission line. Okay? The one dipole that you see, what you feed it with is a coaxial, this one. You see here the connector, the metal, it comes like this one. Have you seen how this looks? If you take it out, have you taken any? You can see it after. It's like a coaxial line, all right? So it has a central, like the ones we've seen, the coaxials. It has a central conductor, and around it has a material, and around that has another conductor. Both of them are like that. This one connects to the center conductor of the coaxial. So instead of having it like that, which is ideal, the way I have put it down here, how do they have it? Simplistically, there is a coaxial here, and then it comes here. Oops, not exactly like that. It's not like giggly, but it's like it. All right. So the way you see it here, the coaxial comes from the bottom of your device. And then here is your monopole. This is called a monopole instead of a dipole. This is dipole. This is monopole. And they both are identical. It's just that the ground creates, as you find if you take a class on antennas, the ground practically creates an image that practically produces the other part of the dipole. But it's a monopole, like this. Why does this have, okay, of course, everything that radiates is called the equivalent. Equivalent of this circuit here is gonna be a resistor, like what I gave you, and a capacitor. And why? Well, the resistor, we said, it's like everything that is radiated, all right? Whatever goes here is the equivalent of a resistor because it does not turn, the resistor does not turn it into heat, but it turns it into radiation and you lose it, all right? So the equivalent resistor. Where is the capacitor coming from? What did we say when we did electrostatics and magnetostatics, electrostatics specifically? What did we say about a coaxial? What happens around here? Do we not say that there is a capacitance? All right, at the end especially, there is a capacitance because there are charges that come and accumulate at the end as you feed the dipole. And therefore, because of the charges that are accumulated right at this intersection, right at this junction between your coaxial and your monopole, there is a parasitic capacitance there. And that's what you see here. And these parasitic capacitances are important. You have to take them into consideration. So when somebody comes here and tells you, here's, let's assume you wanted to design that one, all right, this one. Somebody is giving you that and it tells you that this monopole here, it will have this radiation resistance, R sub L, which is 80 ohms, and then it's going to have a parasitic capacitance because of this, because of the feed here with the coaxial. And now you say, now you understand why it is important to understand that, all right? Why a coaxial creates a parasitic capacitance, because there are all of these charges. We saw that. How the charges go around the surface of the inner conductor and then the outer conductor create a capacitance, all right? So that is the capacitance is given to you. So with this small here, so you can get a sense of what it is, that why do you have a capacitance in an antenna? Now what we have seen is that we know, now you have to remember what we know. We know the voltage, we know the maximum power, we know this length, we know this characteristic impedance, we know the resistor of our load, we know the capacitor of our load, we know the frequency. And then we need to find D2, D3, and D4. All right? Okay. Now, of course, I want to do all of this. There are, number one, a question that people ask, and many classes, which is there only one solution to this problem? And the answer is no. In every design, there are more than one possible solutions, all right? Like you design a house, there are many architectures. The same thing with circuits. You design a circuit, there are many possible architectures. What conditions that are imposed on you will specify the best design will be a lot of conditions which now we have not listed, which is primarily, what kind of circuit do you have? Is it gonna be something like that, or is it gonna be something like this? Do you wanna spend a lot of money, or you wanna spend less money? All right, that is gonna tell you what kind of materials you're gonna use, what kind of application processes you're gonna use. Do you wanna do something in a 3D printer that people can develop that today using 3D printers, or you wanna go into the clean room and develop your circuitry, which is a lot more expensive, because you also have to send it out of the country to do it nowadays. All right? So on the basis of that, people will tell you other things that you have, that will force you to decide which, and that's what designers do, because also it's like a designer is like an architect. All right, they give you all of these things, and some architects do a great job, or some other architects don't do a good job. But that's how the design is. For now, so answer one, no, there are many other ways of solving the problem, and then you may find another way to solve the problem, and that will be absolutely okay. So how I'm gonna solve the problem depends on how I think I should solve it right now. And since no other constraints have been given to me, then more than one solutions will be acceptable, all right? So if in the final, I give you something like that, or a portion of this, and then you come with different solutions, you will be fine, as long as your approach is correct. Okay, now that you did these two things, what is the next thing that we are gonna do as we discussed? We have to develop an outline for the solution of the problem, all right? Remember, we said that we have to outline the problem. So outline, in fact, the solution of the problem. So we have to write here our outline, and you will have to write it. In the final, I will ask you to write the outline of your solution before you provide your solution. Okay. Now, at this moment, I will ask you, as I will do in the final, to solve this problem using a Smith chart. All right, when I tell you find the matching condition here, I will specifically say here, use a Smith chart. I would not like you to write equations down. So now you know that you have to develop a Smith chart. Okay, before, let's try to think how you would solve the problem. Number one, what do you have? Let me put the letters here. A prime, B prime, C prime. Okay. In order to get your source to deliver all of the power that it can deliver to your load, number one, your solution should not incorporate any resistors. All right. So the solution that you're going to provide will not have resistors, will not include resistors. You cannot add any resistor in your circuit, because if you add them, they will take part of the power. Number two, okay, whatever I do when I define D3, D2, I'm not gonna, I have not asked you to add anything into your circuit. So that does not mean that you cannot add, but I'm not asking you, which means that there should be a solution without adding anything. Otherwise, I will tell you at the stop, do something, all right? I will give you guidance. So obviously, I can solve this solution, I can solve this problem without adding anything, all right? And that will be preferable. But what if I don't add anything? How will I get the maximum power to come into my circuit and eventually to the antenna? By defining D2, D3, and Z1. So the reflection coefficient here, as I'm looking towards the load, is 0. So I would like to make this one, in fact, let me move Z further out, Z not here. I would like to make this one equal to 0. Why is that? If I make it equal to 0, then number one is going to be 0 everywhere on my line, all right? So it's going to be 0 right after immediately. If I'm sitting right here, somewhere right here, I will see a 0 reflection coefficient, which means that my source is going to deliver everything, all right? Because I see the source is going to connect, the power is going to start going down the line, and when it arrives at BB prime, it's not going to see a reflection. So it's going to be absorbed by the rest of the circuit, okay? That's what it means. So reflection coefficient there has to be 0. Why did I not move that into the red transmission line? I did not move it there because obviously I don't even know what Z1 is. If I have to find Z1, I'm not sure that Z1 is going to be Z0. Z1 may be something different than Z0, so I cannot control what happens in the red line and in the green line. Since I do not know D2, I do not know D3. I know, since I'm not asking you to add anything, then I know that definitely, since I have Z0 in the green line here, my reflection coefficient at the load is not 0. Okay? Since my load is RL and has a CL, my reflection coefficient here is not 0. That I know. I don't have to do much work, all right? Z naught is 50 ohms. The other is different. So obviously there is a not 0 reflection coefficient, which means, okay, whatever, I cannot do much. It's all set. Here now with Z1 and D2, I don't know what they are. So the only place where I have some certainty about how the line is, I have the characteristic impedance and I have the length, is in the blue section. So that's where I'm trying to set the reflection coefficient at BB prime to be 0. Okay, so I will then, number 2, I will have to make gamma at B prime to be equal to 0. Okay. That implies, what does that mean? That implies that the input impedance, which I'm gonna do with red, the input impedance here, like this, how much is this gonna be for the reflection coefficient? Pardon me? Yes, Z naught, 50 ohms. That implies that my Z input at B prime will have to be 50 ohms. I will have to make it 50 ohms. So for this one to happen, I will have to make Z input at B prime to be 50 ohms. That's the other thing, all right? So now I'm getting a little closer since I know how much my Z input at BB prime has to be 50 ohms. I don't care about the blue anymore, all right? So now I'm concentrated on the green, on the red and the green sections. Okay, now, if my Z1 is, since I cannot add anything, that means forget about stubs, all right? Because stubs is something that you will have to add. Now, what is the other thing that I remember from all of the things that I've seen? I remember the concept of a quarter wavelength transformer. What is the concept? So I'll make here a note here, because that comes to mind with me. Since I cannot add stubs, what other things can I have into my toolbox? I have the quarter wavelength transformer. So a quarter wavelength transformer, quarter wave, really we call it for simplicity, transformer, is nothing else but a section of a line, transform, excuse me here. It's a section of line, okay, so a transformer, it's a section of line, all right, that has the following characteristics. If this line has a real load at the end, that is the specifics of the quarter wave transformer. If it has a real load at the end, here, real, say RL, just so we remember it's real. And then I would like here to create an input impedance, which is also real. If I want to create a Z input here, which is also real, all right, then I can find a quarter wavelength section of a line whose characteristic impedance Z1 will be the square root between these two real, RL and Rin. And then this line, which has a quarter of a wavelength length and a characteristic impedance, which is the square root of these two real numbers, impedances, then I know that this line will take a real load, RL, and transform it into another real load, Rin. All right, so we know that. Since I know this, then I say, what if I can go to the green line here and I find the length of the green line, so my input impedance here is real. If I could do this, and this input impedance here is real, then my red section can be a quarter wave transformer. And then immediately I will be able to find Z1 and D2. All right, so the whole, so now I'm writing it here. I'm saying, therefore, 3. what I need to make as 3 is to find the length. Find the length D3. So the input impedance at C prime is equal to a real impedance, R in at C prime. That's a condition, otherwise I could not make the red section a quarter wave, all right? And why do I want to go there? Because since I know the quarter wave, then I can shorten my solution to the problem. The only thing practically that I will need to do is to find D3, so this is real. So practically all my solution reduces to this. So if I find D3, so my input impedance to the green line is real, then immediately I know what is the red section. And the red section is going to be a quarter wavelength transformer. And I immediately can identify its characteristic impedance from this expression. Do you agree with that thinking? Okay, so now I have outlined my solution. Now I know what I'm supposed to do. Yes.
I never really, sorry for interrupting, but would, like, if it was a lossless, does that mean the characteristic is zero, or is that something else?
The characteristic impedance is always real. All right?
If you have a, what would a characteristic impedance be zero?
There is no such a thing.
Oh, okay.
All right, there is no transmission line that has characteristic impedance 0, because characteristic impedance, if you remember, we defined it as the ratio of the incident voltage wave, V0, over I0, which means for that to be 0, then you have 0 voltage or forces. There is no such a thing, all right? That means the two conductors are, one touches the other. If you remember the parallel plate waveguide or the coaxial, it has a characteristic impedance, if you consider as transmission line of 0, if the two, in some point, the two conductors, they collapse one on top of the other. That's 0 character, but that's not a transmission line, all right? Practically, it's a short everywhere. It's like shorting. Okay.
What determines whether something's lossless or not?
The materials themselves.
Okay, so Z1 is not dependent on, or Z1 isn't solely dependent on the
Z naught does only depend on the geometry. But if, say, you have in real life, everything is lossy. All of the materials will have some kind of loss. All of the conductors will have some kind of loss. The thinner the conductors, the more the conductor loss. All right, you have to make them very thick to avoid that. Who wants to put thick gold or copper, which is extremely expensive? So people try to put the cost down, and then they have, and also it's very difficult to fabricate in the clean room metals that they are very thick because they do them by deposition. So they put molecules, you put molecules, all right, one on top of the other. It takes hours to put something like that to create a conductor. So people will barely make it, so it's not very lossy, but it's going to have losses. So in reality, everything has losses. The losses, however, if they are low, because high losses, who's going to use a transmission line with high losses? All right. So low losses do not affect the characteristic impedance. They mostly affect the propagation constant, beta. They will introduce, like gamma we call, they will introduce an attenuation factor. But characteristic impedance in like practical transmission lines is always real. Yes, and it depends only on the geometry. Only. Okay. Sure. Now, you also know that you have to use the Smith chart. Since we have to use the Smith chart to solve the problem, what else do we have to do? Normalize, exactly. So now in our outline, we have to normalize. Practically, the only impedance we have to normalize is ZL, all right, which is RL plus J omega CL. In fact, minus, excuse me, it's capacitor, minus J it was inductance, minus J 1 omega CL. So now I will have, I know RL, I know CL. Therefore, I have to find omega CL. All right, so my ZL, so solution now. Now I'm ready to go to the solution. I'm starting with 4. All right, so the interesting thing is that after you outline the solution, you always start from the bottom of the solution, all right? Because the solution is kind of abstracting your problem. In the outline, when you try to think how to solve the problem, you always start with what you have to accomplish. And then you say, to accomplish that, I have to do this. To do that, I have to do something else, all right? So eventually you come down to where you're gonna start your solution with. So 4 here, 4 is the place where I'm gonna start. All right, so here I have to find, first of all, ZL. ZL is 80 minus J 1 over 2 pi F CL. Let's try to find how much that is. 2 pi, F is 10, gigahertz is 10 to the 9. CL, let me see if I gave you a good value, because I may have to change it if it's too small, is 0.5, 10 to minus 12. 0.5, 10 to minus 12. I may have to change the 0.5 if it becomes too small, all right? So let's see how much that is. This is 1 over 2 pi FCL. Oh, no, excuse me. Sorry, I'm doing 2 pi. This is 2 pi FCL. Okay, so this one and this gives minus 3. This one and this gives minus 2. So practically I have 2 pi times 0.5 times 10 to minus 2. And I have to tell you, this is a very small number for a reactive. So to change that, I'm going to try to change this and make it 50 instead of 0.5. All right. So I'm going to change that and make it 50 picofarads. To be just kind of a substantive, capacitive, reactive load. So 50 here. So I'm going to put 50 here. 50. So practically with 50 here, it's going to give you 2 pi times 0.5, which is going to be, it's still very small. So most probably let's put 500. All right. See how I make problems now. 500 to make it big. Just so it's not, I'm going to do something on the Smith chart. 500. So here, that's going to be, all right, that makes, all right, so that's going to be more substantive. It's going to be 10 pi, which is going to be 10, but there I divide, so it's going to be 30. That will be, I think I was right with the 0.5. I'm sorry, let me, yeah, because I'm going to invert it. So I don't want to, I want to have a substantive reactive part. Okay, so I apologize for doing that. 0.5. Okay, and all right, and then I will go back and change this to 0.5. So I was correct. My gut feeling, 0.5. All right, and that will be pi, practically. Even that is kind of pi 10. It's also, we have 100 there. Okay, times 10 to minus 2. So it's going to be pi divided by 100. I'm right. Okay. So it's going to be 3 point something. I will leave it like that for a moment. And then, so ZL will be 80 minus j 1 over pi divided by 100, which is going to make it now 80 minus j. 100 by pi is about 30 something. Let me see how much this is going to be. 100 divided by pi equals 31.8. Okay, we'll make it 32 approximately. And that is in ohms. Now that's reasonable. Okay, so that was good from the beginning. All right, now 4. I'm going to 3. In 4 I'm not done. I have to normalize. Now I have to normalize also ZL, which means I have to divide it by 50. So 80 minus j 32 divided by 50. And that's going to be 1.6, I believe. And then 32 divided by 50. 0.64. All right, and that's just a number. Since I have it normalized, it's just a plain number. Yes.
And that xenon is based off of the
Yes.
characteristic impedance to the right of CC prime?
Yes.
Okay, not the one with the
No, because now you start from the load. You remember? So I'm right on the green. I don't see anything from the rest. So I'm gonna do, you remember what I need to do? Number 3, I need to be on the green line, and then I need to move from the green line where I am. See, I am right here. I'm right here. So I normalize with respect to Z naught. I need to move from the load, whatever my load is now normalized that I found. I need to move by a distance until I find a purely real number, which is going to be my input impedance normalized at that point.
Why did it have to be completely real again?
Go ahead, Justin.
Why did it have to be completely real again?
It has to be completely real because of this concept of the quarter wavelength transformer. The quarter wave works only if it has a real load at the end and can transform it to a real load. All right, so from one real load transforms to another. And if I know the real load, and if I know what I want it to transform to, then I can find Z1. And the length is always quarter of a wavelength. All right, that's why I'm gonna use that concept, so I don't have to go, since I don't add anything to this to design it, I'm gonna use the quarter wave concept. For me, whenever I can use it, I use it because I don't have to design anything, it's ready. All right, it gives me the length, it gives me the characteristic impedance. I don't have to do anything else.
I'm still not sure why exactly you needed the lambda over 4 length.
That is how the quarter wave is. A quarter wave, and it is, we did it as an example in one of our solutions. It has to be only a quarter of a wave for this to transform a real load to another real impedance. It can only happen when it is a quarter of a wavelength long and when the characteristic impedance is the square root of the two real impedances, the load and the input impedance.
Okay. So we're trying to get an input impedance that's completely real.
Yes, and what else in addition to that will have to be? Remember what we said? We have to make it 50 ohms. So that's
Okay.
that the red one is going to be your quarter wave transformer. Okay?
Okay.
All right. Okay, so now with that, we're going to go to the Smith chart. On the green, in the green, we are along the green line, if you remember. So now I'm going to go and take and find a Smith chart somewhere. here, copy, and I will clean it up, of course. All right, so here, paste, and give me a second to clean this up. Okay. All right, now we normalize the load. We are on the green line. Remember, we are on the last section. All right, so just to let me remind you, we are right here. And in fact, if I copy this, copy, and take it next to the Smith chart, right here, paste. So you remember what I need to do? I need to find D3. So this input impedance here on this transmission line at CC prime is real. That's all that I'm asking. And in fact, let me move it a little further down here. All right, that's what I'm trying to do. The rest I'm forgetting. So now I know what is my ZL for that frequency. I have found that and I have normalized it. And what I found when I normalized was 1.6 minus J.64. I found that to be 1.6 minus J.64. So now I have to find this line, this impedance. I have to find it here. So 1.6, I'm gonna use red, this one and this one. Okay, 1.6 is here, and I will, all the points of this circle have 1.6 real part, okay? Now I'm gonna find the 0.6, what did I say? 0.64 reactive, it's negative. So I'm gonna go to the lower part of the Smith chart, and I'm gonna find minus 0.64, which is somewhere here, and with a green. And the intersection between the two is gonna be my load. That's my ZL. And then also what I can do to remember, I will write it here. This is my ZL. ZL normalized, which is 1.6 minus J.64. So now that I found it, I'm going to erase these circles. For your exam, if you have anything like this, you can keep them, all right? So I can see what you're doing. I'm removing them here so it becomes cleaner. All right, now I have to move on the green line. To move, what do I have to do? I have to write the circle of this transmission line, all right? Then I cannot move otherwise. What is this one? Is the circle that has center, the center of the Smith chart, and goes through this purple point. True? Okay, so I'm gonna do it now. Green. And I'm gonna do it a little thicker, so we'll see it. There. Well, not right. It. Okay, you have this one also. Oh my God, this one has quite a character, this thing. Whenever, whenever I think probably he says, well, the heck with you right now and your circles. Okay. the old days when we had the beginning of times when we had Word, it would just in the middle you would write something and it would just crash. Microsoft Word Office. And I remember we had to save it personally every 5 minutes. Otherwise, every time you would write more than 5 minutes, it would crash, it would not keep anything. That was, oh my God, anyways. So at least now. All right, so now, how are we gonna move? We're moving only from the load towards the generator, always this. So we are moving along this direction only. And if we move like this, and I will start moving, where am I gonna stop? That's the question. So from here, I will move, and you're gonna tell me when where I'm going to stop. I have to stop to a point that has only real. So tell me before I get there where to stop. Do I stop?
One more.
Ah, yes. You have to give me warning. I cannot stop immediately. All right, so I stop there. Now, if I were to go another half circle, I could go to the other end of the circle, which is also real. But that implies that I go for too long, and I don't want to use lines which are too long if I have to, because the real lines will have losses. The longer the lines, the higher the losses, all right? So,
You always have to travel counterclockwise, like after.
no, you can't. Only there, only because that's how you go towards the generator, right? Here, to be able to find, I'm moving this way. All right, so I'm starting here and I'm moving until I find this point where it's real. So I have to move towards the generator, towards the source meaning, which is that direction here. You see it? So that's how I move. And then the arrows show. And I suggest you do the arrows because sometimes in the middle of things, you may forget which direction you have moved. And instead of going from this point here to the other point, from ZL to this other one, which in fact, this one here is gonna be your Z in at CC prime. Okay? So that's where I stop. Now it's real. And as a matter of fact, I can find it and it's exactly 0.5. So this one normalized is 0.5. I found it. So if I move this much, I can create my Z input at CC prime to be 0.5, which in reality, how many ohms is that? Yes. So Z in at CC prime, if this is 0.5, that implies that Z in at CC prime will be 0.5 times 50. So it's 25 ohms. Now, what else do I need to find from this line? I need to find the length. All right, while I'm doing this, I need to find how much distance I'm moving from where I am, ZL to Z in. So how do we find the distance? Now, we connect the center with this point. All right. And then we see where it intersects the green, the yellow rim. So here, and we read exactly what number that is, and I will write it, and it's 0.294, and is in lambda. And then the line between the center of the Smith chart and the other point, Z input, the one that I stopped at, it's also this one, obviously. And the point here that I'm stopping is 0.5 because I'm going all around the circle and I'm coming to 0.5, all right? So the point here, and I'm going to write it. This point is 0.5 lambda. So how much is the distance between the 2 points? That tells me that D3 will be 0.5 lambda minus where I started. It's where I stop minus where I started, which is 0.294. 0.294 lambda, which means that 651. No, 2. 4 was 6, 9, 5, 5, and then 2. Where is that? That's too much. 206, right? Thank you. I was thinking it's more than half of the circle. Okay. So I found this. So I'm done with one unknown. So now that I've done this, I'm done with the other thing because now I know. So at this moment, I have, remember the outline where I am. Outline. I've done 3 and 4. Okay. So 2 happens immediately. So I've done 3 and 4. So I'm done with 3. 3 plus 4 are done. 4 is done. So now with 2 from my outline, I have the red line practically. I will have to create a quarter wavelength transformer. All right. So from 2, which is the quarter wave, and to just remind you, this is the line now I'm talking about. This line is going to be the quarter wave. All right. So I'm going to go down here and I'm going to have the D2, since this line is quarter wave, D2 is going to be, and in fact, why do I not just take a picture, a copy of it here, copy, and go down here and place it, paste. Okay, this is the line I'm looking at. And I have found that my load here is 25 ohms. In fact, it's just this one, all right? I know that this is a quarter of a wavelength, so I found that. All right, so I have this in place. And now, since I know that the line that I wanna transfer 25 ohms to what number? To what real load, real input impedance? What is that, CC prime? How much do I wanna make this one? You remember, according to my outline for the solution? Here. To make my reflection coefficient at that point on the line here, to make that 0, the impedance I see from that has to be 50 ohms. You agree? Okay. So now I'm gonna make Z input equal to 50 ohms. That's what my outline told me from the beginning. So that gives me Z1. So Z1 is gonna be the square root of 25 times 50. And that is gonna be in ohms. So now I solve the problem. Now I have everything, 25 times 50, and that square root is 35.3. So now I found that. See? And I'm done with the solution. So what I want you to remember, always very systematic in the solution. You always start from writing what is given and what you have to find, and then after that, you write the outline. Without your outline, there is no way you're going to solve the problem. And with the outline, you start with what you have to accomplish at the end. So you see, one, first of all, that will not include resistors. That's part of the understanding, all right? If you are to include resistors in a matching problem, you are gonna lose all the time. So no resistors in any matching problem. Then I wanna make this equal to 0. That's where I started thinking, how am I gonna make that equal to 0? And then I remembered the quarter wavelength transformer because it's an easy solution. Since I need to find Z1, if they had given me Z1, I could not apply the quarter wave. Do you understand that? I mean, it's because Z1 is undefined and I can control it. That's why I was thinking of the quarter wave. So I thought of the quarter wave, and then I realized to apply the quarter wave, then I have to find a real input impedance in the last section of my problem. That's where it drove me into deciding that my input impedance there has to be real, in my input impedance at CC prime, which then gave me an opportunity while I was looking for this input impedance to also find D3. And that's how we solve the problem. The moment you have the outline, look at the solution. The solution is from here.
It's 4 o'clock.
Yeah. The solution is from there down here. It's not very long. The moment you know how to solve it, the moment you know the how. And this is true. So we have to go. We have, for any questions, we have problem solving session today in about half an hour. So please come between 4:30 and 6:30 anytime. Okay? I have to go because there is another class starting. Thank you.